sac121 number 3 is a statics problem. We'll get started on that by drawing a free body diagram of the object under consideration, namely this bar. So get the bar in there, and then start indicating the forces acting on it. This pin connection can keep the bar from swinging out away from the wall or moving in toward the wall, and it can also keep it from falling down or moving upward. So the net force exerted by the pin could be in any direction. I'm going to indicate its components as px and py. So we'll find the components individually and then add them together vectorially to get the net force on the object. Alright, we've got at point P, we've got a weight force acting down right at the center. I'll call that W. And then the rope exerts a force on the object away from the object along the length of the rope. So I'll call that one T for the tension in the rope. Now we're going to set the net force on this object equal to 0 in both the upward and the downward directions, and the net torque, I'll calculate the torque about what I'll call point P. Because I got two forces acting through that, they will make no contribution to the torque. So they'll be pretty easy to deal with. When I go to get the torques due to the other forces, like W, I'm going to need the moment arm. So let's indicate some distances on here. We got an angle, I'll call it theta, where theta is equal to 24 degrees. And the moment arm for the weight factor will be this distance right here, which if I call this distance L over 2, and this distance L for the length of the entire rod or bar, then this distance, I call it our perp W. Our perp W is going to be equal to, let's see, I'll divide it by L over 2, and that's adjacent over the hypotenuse, so that'll equal the cosine of theta. So R perp W is equal to L over 2 cosine of theta. That's going to come in handy when I calculate the torque due to W. And similarly, if I call this R perp for the tension, I'll have R perp for the tension is the adjacent over the hypotenuse L, and that's going to equal the cosine of theta as well. Multiplying both sides by L, I got R perp for the tension is L times the cosine of theta. Okay, I think I'm ready to start summing forces and torques. I think the simplest one is going to be the sum of the forces to the right. Their simplest equilibrium condition. Net force to the right is equal to 0 because the object is not accelerating. And this just tells me that px is equal to 0. because that is the only force to the right. The next simplest one, I'm going to go with the torque. If I sum the forces in the upward direction, I get Py and T, Py as well as T in the equation. I'll have two unknowns, but I see the torque is only going to involve the tension and the weight. If I sum the torque about point P, I'll call counterclockwise the positive direction, and that's got to be equal to 0 as the object is experiencing no angular acceleration. So I'll have the torque due to W, which will tend to rotate things around clockwise, and it'll be R perp W times W with a minus sign because, again, it tends to rotate things around clockwise, and I said I'm calling counterclockwise the positive direction. T would tend to rotate the bar around counterclockwise, so it comes in with a positive, and I go plus R perp T times T equals 0. And then we found these expressions for the R perps. This is minus L over 2 cosine of theta times the weight force is mg, and then plus R perp T is L cosine of theta times the T where T is sought. That's all equal to 0. That's interesting. The cosine of thetas cancel. The L cancels. L over L is 1, so that becomes a 1/2. What I've got here is T, and then I'll add the 1/2 mg to both sides, so T is equal to 1/2 mg. So we can actually get a value for the tension already. We're given that the mass is 26 kilograms, so this is 1/2 of 26 kilograms times 9.80 newtons per kilogram, or T to 3 sig figs. I'll go ahead and multiply that out on the calculator. First T, just what the calculator gives, 127.4 newtons, and then if I round that off to 3 sig figs in that, let's see, how many sig figs do I want here? It's actually 2 sig figs. Everything's given to 2 sig figs, so I'll call that 1.3. I'll call it 0.13. kilonewtons. And then the direction for the tension is upward. So the tension force in the rope, given the direction, I'll indicate that it is a vector, 0.13 kilonewtons in the upward direction. Now, we're in a position to get Py. What I'll do is sum the forces working off of this diagram in the upward direction. It'll give me a Py minus W plus T equals 0. So actually I might have room for it over here. Sum of the forces in the upward direction is going to be equal to 0. And working from the diagram, I've got Py upward minus W plus T equals 0. At this point, T is known, so I can just solve for Py. That's W minus T, or mg minus T, which is the 26 kilograms, 9.8 newtons per kilogram, 9.80, minus the 127.4 newtons. I'll use my intermediate results here and get Py is 26 times 9.8 minus 127.4 equals, I get a 127.4. Okay, we get a little vector addition problem to do to get the total P. It's a trivial one in this case. I add Px and Py to get P, but because there is no Px on this diagram, I indicate a zero-length vector to the right, or didn't indicate anything at all, but P and Py are identical, so P, the vector P, is equal to point. No. 1.3 kilonewtons upward. I'm going to round it to 2 sig figs, what I was starting to say before.